Physics 1D, Modern Physics, where the real fun begins. Hello everybody, this is our first lecture of 1D. We have made it through 1A, 1B, and 1C. We're now finally arriving at the last part of the 1 series, which is Physics 1D. So let's do a quick review first of what we have accomplished so far. In the Physics 1 series, we started with Physics 1A, which is classical mechanics, Newton's second law. And then in 1B, we continued with the applications of classical mechanics and went on to thermal physics. And in 1C, we study electricity, magnetism, and optics. All of these subjects are referred to as classical physics. And as you know, classical physics refers to the body of knowledge of physics that humans have accumulated all the way from prehistoric time to about 110 years ago. So that was a long time in between, and we did learn a lot. For example, in 1A, we learned to calculate how long it would take for a ball to roll down an inclined plane without slipping. Right? You recall that. But you probably would wonder, why do I want to know how to calculate that? Would I ever use that in my work? Well, you have already studied that, so I can tell you the truth. And that is, more likely than not, you're not going to be needing that kind of knowledge specifically. So why do you have to study that? Well, if you think of physics as a mansion, or more precisely in our 1 series, if you think of each of the classes as a floor, then it's a 4-story building, right? And 1D is the 4th story. It is really where the good stuff begins. But you cannot build a 4-story building starting from only the 4th story. You have to build from the ground up. But we have built the previous 3 stories, so now we are doing the real fun part, modern physics. Modern physics refers to the knowledge of physics that we have accumulated since about the beginning of the 20th century, about around 1900, and it's relatively a short time compared with classical physics, but we have learned so much in this short amount of time, and it has brought so much good stuff to us in terms of applications. For example, how do you ever wonder how your iPod works, your iPhone, modern cars, computers, you name it? You know, all these modern gadgets that we enjoy for granted, they all have to do with modern physics. So, what is modern physics? What are the things we do to study in modern physics? Well, let's look at this diagram. I have made this diagram up, and here we have a horizontal axis which refers to the size of the system that we study, how big it is. And the vertical axis refers to the speed of how fast, basically how fast an object moves. Okay, in classical physics, we were pretty much limited to what we can see and what we can feel. So size-wise, we're looking at something, starting from the human body size, which is around a meter. We can go up to maybe, a few thousand miles, or even a little bit more, think of the Earth and the Sun, even the Earth to Sun distance. We can look at the solar system, something quite big. And on the other side, we can go down to maybe a millimeter, a micron, all these things, they still within reach. Okay, classical physics is valid over a vast range of size. But what if you go further down? What if you go further down this way, size, to something so small that our eyes simply cannot see, even with a powerful microscope, such as a nanometer. You know what a nanometer is, right? That's 10 to the negative 9 of a meter. It's very, very, 1/1000th of a meter. Or you look at things that move very fast, okay? Well, now we're not talking about the speed of sound, which is nothing. The speed of sound is nothing. We can routinely fly faster than the speed of sound. And you don't see anything strange, do you? But we're talking about speed of what? Yeah, it's the speed of light. So you go that way, okay? You venture outside the normal speed that we experience. As you go to something really small or to something really fast, we're going outside the comfort zone of classical physics, which is this region, okay, which is this region. Somewhere lies a boundary where classical physics still applies, beyond which classical physics starts to fail significantly. Now, of course, there's a gradual process. So people have learned that as you look at something very small, or you look at something very fast, what we learned before in classical physics no longer works. So a new theory has to emerge to take its place. And so we have this zone here, either something very fast or something very small. And that is the realm of modern physics. Okay? So this is classical physics. So you see, there was nothing wrong with classical physics except we could only apply it to, things of normal size and moving with reasonably slow speed. But as we venture beyond those boundaries, we find that classical physics failed to give us the correct prediction as how things work. So we have to study a new theory. Now you might think that since we do live in a macroscopic world here, in this region, we shouldn't really have to be concerned with something really small and something really fast. But, nothing can be further from the truth. For example, even though the human body is much bigger than one molecule, we are made of many, many, many molecules, and the behavior of these molecules can affect what happens on a much larger size, and we all know that. So therefore, in order to understand physics better, we have to look at something very small and something very fast. It is not just important theoretically, it also provides us with extremely rich variety of applications. Like I said, anything in modern electronics, for example, is tied to our study of the very small world. And relativity deals with something very fast. I'm sure you have heard about those things as well. So there are two major areas of modern physics that we'll be studying. One is, as you go very fast, that's relativity. Okay? Relativity. It's, of course, forever associated with the great name Albert Einstein, the greatest physicist of the 20th century. And then this side, as you go very small, the theory that applies to the small world is called quantum mechanics. Quantum mechanics is not associated with a single physicist. It is associated with a number of great physicists, Einstein being one of them. And we're gonna start with our study of relativity first. It's gonna be our first chapter. And then most of the time, we'll be actually studying quantum mechanics, the world of very small. And of course, you might imagine that what if you go this way? You look at something both very small and very fast. Well, you can imagine that if you do that, it will require both consideration of relativity and quantum mechanics, and then we're entering the realm what's called relativistic quantum mechanics. Make sense? Okay, now, on the other side, it's often easy to ignore that, and that is, if we go that way, very large. We're not talking about the size of the sun or even the Earth to sun distance. We're looking at something even bigger. We look at the structure of the universe, the ultra large. Okay? Clearly, Newton's second law was derived from something much, much smaller. Okay? So we shouldn't be surprised if when we go that way, Newton's second law or the entire classical physics fails. And as a matter of fact, as we look at something really large, indeed, we have to look at a new theory as well, and that is what's called general relativity. This is only called special relativity. Both, of course, was a brainchild of Einstein, and we're not going to study too much about it here in this course, but we're going to study a lot more about relativity and especially about quantum mechanics. So the whole idea is that we are going to venture out of the comfort zone of classical physics to look at high speed, small size, or even large size, and we're going to look at the new physics, modern physics, that revolutionized our way of looking at things, and it also brought us an incredible amount of great inventions, making modern physics the dominant science of the 20th century. Okay, so before we actually start our study of modern physics, I want to talk about a couple of interesting things that has to do with our mindset when we study modern physics. You know, intuition is very important in science, especially in physics. But where does our intuition come from? Our intuition mostly comes from common sense, from our daily observation. Okay, we look at it and say, you know, this makes sense. Why does it make sense? Because I've seen it before, you know, or haven't seen it before. It looks awkward, therefore it doesn't make any sense. So intuitively, it must be wrong, and so forth, right? And our intuition played a great positive role when we studied classical physics. For example, if you look at, if you do a calculation of the speed of something, you find the speed of a car to be, a few miles per second, you know that's something wrong, right? It cannot be that fast. You must have done something wrong in your calculation. Okay, so intuition tells you this must be wrong. But does intuition still work in modern physics? Well, it does to some extent, but we have to be more careful here. Because again, we're venturing outside our comfort zone. Okay, so we're not deriving everything from common sense anymore, because common sense comes from daily observation, from our living experience, which we do not have when it comes to traveling near the speed of light or living in the microscopic world the size of a molecule. We don't have that kind of life experience. Therefore, we cannot always derive our results from common sense. So our intuition often does not work anymore. Okay, so this is something you got to be pay attention to. So be prepared for surprises. Surprises means results that look paradoxical, it look wrong, because it doesn't conform with common sense, and it could still be right. Okay, so you got to keep an open mind. Just because something doesn't agree with your common sense does not necessarily mean it is wrong. It only because our common sense may not apply here. We got to keep an open mind. Okay, now, another thing I want to talk about is, why do we study modern physics at all? Well, besides the obvious reason of seeking new knowledge, another great thing about modern physics is it's got so much applications. Okay, applications of modern physics. Again, like I said, it is the dominant science of the 20th century, the century that just went by. The dominant science. No other science has produced that much important results, had given us that much important applications than modern physics. Entire industries were born with the inventions, with the discoveries in modern physics. For example, modern electronics. Okay, modern electronics. Anything that has to do with electronics these days, you know, iPod, iPhone, modern computers, HD TVs, anything that has to do with electronics. At the core, at the heart of the technology is a silicon chip, okay? And silicon chips are based on semiconductor physics, which is part of modern physics. And like I said, entire new industries were based on modern physics, computers. Without computers, of course, there won't be any internet. Entire nuclear physics, the entire nuclear industry is based on nuclear physics, which is part of modern physics. The airplane industry. What about lasers? Okay, and countless other things. All these things have to do with modern physics. Without modern physics, none of these things would have existed, and you wouldn't be watching this video, of course, because, you know, it has to do with electronics. Okay, now I just want to single out nuclear physics a little bit, okay, just a little bit, to discuss the importance of real-world applications of modern physics. Nuclear physics has to do with the physics of the atomic nucleus, and its great significance lies beyond just our understanding of the nucleus because of the energy content of nuclear physics. The great formula, the single greatest formula in physics ever discovered in the 20th century. I'm sure you know what it is, right? What is it? Or it is E equals mc squared, okay? So if you can somehow manage to change mass of something, which of course is a brand new concept, how do you change mass? We're going to talk about a little bit later, okay? But you somehow change mass, you can convert that mass to a great amount of energy because you have to multiply the mass by the speed of light squared, which is a huge, huge number, okay? And this is the theory behind the energy stored in atomic nucleus. So through nuclear reaction, we can unlock a tremendous amount of energy, and that is nuclear energy. And nuclear energy, just like anything else in science, is always a two-edged sword. You can put it to good use, and sometimes people also can put it to bad use. And nothing is a better example than nuclear energy. Humans have built atomic bombs or even hydrogen bombs based on our study of nuclear physics. But we have also built nuclear power plants, which is a positive use of nuclear energy. Now you might say, well, nuclear energy, nuclear power plant these days, that's almost a dirty word because of, all these bad accidents, right? But accidents happen. You don't just stop driving because you might get an accident, right? Just want to try to improve the safety and so on. The problem is, what do we do without nuclear energy? Well, without nuclear energy, what's the alternative? Of course, fossil fuel is still the main source of energy for us to use. But the problem with fossil fuel, as you know, fossil fuels, it took the Earth millions of years to produce them. It only takes us a few decades to deplete them, okay? The United States has only about 3 years of fossil fuel energy supply left within its own territory. If we stop importing and consuming at today's rate, it's only going to take 3 years before we exhaust all our fossil fuel supply. Okay? And even if you add the fossil fuel supply of the rest of the world, including Saudi Arabia, the entire Middle East, and whatever, we only have less than 50 years left before we truly run out of gas. Okay, so we are going to be the first generation who will have to face this dire consequence. We have to do something before we truly run out of gas. And of course, there are many alternative forms of energies being researched on, such as solar power, wind, and so on. And they all can be very beneficial to us. But at this point, nothing in our near future can replace nuclear energy, because its scale is such that it can, in theory, it can produce enough energy to totally replace fossil fuel. And the fact that nuclear energy is dirty is because we're only using fission as the source of nuclear energy. But fusion, on the other hand, is far cleaner. It mimics the way the sun produces its energy, and we have an abundant source of fusion energy. All these details will be studied in nuclear physics, which is part of Physics 1D. So modern physics not only gave us all these fun gadgets for us to play, it also will play a pivotal role in the energy source of our future. Without that, humans cannot survive, at least cannot live the way we are accustomed to. So it's got glorious past, okay? It was a dominant science. It will continue to be an extremely crucial part of humans' quest of knowledge and our study and our sort of guarantee to our current lifestyle if we want to continue to explore energy the way we have been doing. So future significance, okay? That's energy is only part of it. And there are other things that you can think of, exciting things that you can think of that has to do with modern physics. We have been, for example, miniaturizing computers. Okay, the first computer, as you know, the ENIAC, that was commissioned by the U.S. Navy. That was really big. It's the size of an entire floor, right? But these days, something far more powerful in terms of computing power can be shrunk to the size of a small chip. But in the future, we can do even better. especially with the advancement of what's called nanotechnology, we can conceivably shrink computers further so that computers become virtually invisible. Okay, you may have a computer embedded somewhere, and they're so cheap, so small, you don't see them, but they do everything for you. For example, you can think of miniaturized computers even implanted in your body that monitors your blood flow and so on and so forth. So it gives you early warning signs if you had developed anything and so on. So, it can really do wonderful things that we couldn't be even conceiving before. And from a theorist point of view, okay, I was talking about new innovations, okay, nanometer technology, but from a theorist point of view, if you say, I don't really care that much about applications, but I want to know, okay, can modern physics gives us any new knowledge? Oh yes, it certainly can, in the 20th century. This might be the century where the big toe will become a reality. What is the big toe, or TOE? That is the so-called theory of everything. Okay, this will be a unified theory that combines our knowledge of gravity, electricity, and magnetism, and basically all the forms of forces, okay, all the forms of basic forces into a single unified theory. And this is a so-called theory of everything. With this theory, that at least in principle, we can describe anything in the natural world. Okay, that is called the theory of everything. So this is basically how the universe operates. And, this will be the ultimate theory in science. And humans have existed on this planet for a few million years, and we have accumulated so much knowledge, but never have we been able to write down a single theory that summarizes all the laws and the principles of the natural world in a self-consistent, unified manner, the theory of everything. But this could happen in this century. Okay, so we also talk about new innovations, we talk about energies of the future, and so on and so forth. Those are things that we can look forward to in the 21st century. No matter what kind of science or engineering majors you are going to get into, you will need physics. And in particular, you will need knowledge of modern physics. Okay, so I hope I've convinced you that this is something really good. This is where the really good stuff begins.